Thank you. Thank you, Eunice. Thank you for giving me this opportunity. My talk will be based on joint work with Stanislav Apanasenko, who was a postdoc here in Loughborough. Now he's a postdoc in Italy. Okay, here is what I'm going to talk about. First, I will start with modular forms. So the goal is to give a general, to show, it's well known that modular forms satisfy nonlinear ordinary differential equations. So probably I will say a little bit about the structure of such equations, right? There is kind of these ODEs are known to be invariant under the Lie group SL2R, and therefore they can be expressed in terms of differential invariants of SL2R. I will show you these representations of ODEs for modular forms. Third order ODEs will be invariant under SL2R, and also every modular form satisfies a fourth order ODE, which is invariant under GL2R, weird scaling of the function. And sometimes these fourth order ODEs are simpler than third order ODEs. And then I'll show you after I review this construction. Okay, there is a funny link with the modularity theorem. It's known that every elliptic curve with rational coefficients can be parametrized, uniformized by a modular form of weight 2, cusp form, new form of weight 2. So this is at the center of Fermat's last theorem, this statement. So it turns out that differential equations for modular forms are related to these elliptic curves. And this observation, okay, I haven't seen it in the literature. Right? Maybe you know this topic much better than me. I'm not an expert on modular forms. Maybe in some way this was known, you will tell me. Okay, after I review the construction of these ODEs, I will show some examples of differential equations for modular forms. And finally, okay, I will discuss where these differential equations for modular forms naturally arise. In fact, I come from differential geometry and the theory of integrable systems. And okay, to some extent, to my surprise, modular forms occurred in the coefficients of integrable systems. And I will show you one particular example of this general phenomenon related to integrable Lagrangians at the end of the talk. And if time permits, I will say a few words about differential systems, involutive differential systems satisfied by Jacobi forms. So this talk is based on our joint archive paper, which is here, all right? So, okay. Let's start with a general picture. So suppose that F is a modular form of some kind. It could be classical modular form on SL2Z, or it can be a Jacobi form or Ziegel modular form, Picard modular form. So it can be a modular form of several variables, and so on. Suppose that this is a modular form on some discrete subgroup gamma of a Lie group capital G. So we have a Lie group and the lattice as a discrete subgroup inside this Lie group. So then any such modular form solves a certain nonlinear system of PDEs if it's a function of several independent variables, or an ODE if it's a function, if it's a classical modular form, such that this system, sigma, system of ODEs and PDEs, satisfies the following properties. First of all, this system must be involutive. This means, roughly speaking, the system is overdetermined. Just one function satisfies several differential equations, and these equations are consistent. So involutive means compatible, all right? Second property, the system sigma is of finite type. It means that all, so its solution space is finite dimension. A typical example of an involutive system, imagine a system for a function, say, of several variables where all, say, higher order derivatives of the function are expressed in terms of low order derivatives. It's a typical finite type system. So solution space is finite dimension. Then the system sigma must be invariant under the Lie group capital G. And furthermore, the Lie group, in this means that the group capital G acts on the solution space of the system sigma. So in fact, it's a symmetry group of the system. This means it maps solutions, takes solutions to other solutions. And furthermore, the following property must be satisfied, that the dimension of the Lie group G is equal to the dimension of the solution space of sigma. In other words, the action of G on the solution space has an open orbit. And our modular form F we started with, this F, it belongs to the open orbit. So in other words, F is a generic solution of the system sigma. All other generic solutions are obtained by applying Lie group G to this function F. Right? Still, there may be some degenerate solutions which do not belong to the open orbit, but I will not discuss this in my talk. So let's, here in red, this is what we will discuss today, the case of classical modular forms. So f is a function of one complex variable, tau, which belongs to the upper half plane. The group G, capital G, is a cell to R, which acts in a linear fractional way on the upper half plane. The lattice, the discrete subgroup, is a cell to Z for classical modular forms, or a congruent subgroup. And the system sigma is in this case just a single third order nonlinear SL to R invariant differential equation for this function f of tau. Clearly, in this particular case, all these properties, four properties, are trivially satisfied. First of all, sigma is involutive. Okay, we just have one single third order ODE. Of course, it is consistent. You can't form any consistency conditions, right? It's involutive. Then, system is of finite type. Okay, a third order differential equation has a three-parametric solution space. You can specify at a given point f, its first and second derivative. Then all other derivatives are known because of the equation. So this is also trivially satisfied. Then our ODE will be built in such a way that it's by construction invariant under SL to R. All right? And therefore, the dimension of the group is equal to the dimension of the solution space. In our case, it will be equal to 3. And our modular form will be a generic solution of the system. Okay? So that's a general picture. To the best of my knowledge, there are very few exact results in this direction. There are only some partial results for particular modular forms. There is no general statement proved of this type. All right, but this is what it should be, in my opinion. Okay, so this is what you'll know, modular, but let me go through this still, sorry about this. This is a modular form of weight k solves this, satisfies this equation where A, B, C, D belong to, it's a matrix from SL to Z, or a certain discrete subgroup of SL to R. And in my talk, I will be mainly interested in these congruent subgroups, gamma 0 of n, where C, gamma 0 of n, is a subgroup, discrete subgroup, where C is divisible by n. C is congruent to 0 mod n. So in particular, gamma 0, 1 is just SL to Z. Okay, this you all know. Let me move on. Now, Eisenstein series, it's also something well known. It's a general formula for Eisenstein series. And in particular, we will need E2, E4, and E6. Okay, well-known formula. I'm not stopping on this because you all know this better than me. Now, it turns out that these three particular Eisenstein series, E2, E4, and E6, they satisfy differential equations. They're known as Ramanujan differential equations, first order differential equations of this kind with quadratic right-hand sides. So it's quite remarkable that complicated, highly transcendental objects like E2, E4, and E6 satisfy very simple differential equations with actually rational coefficients, quadratic right-hand sides, right? As far as I know, these equations were known before Ramanujan, but they are called Ramanujan differential equations. And prime here and everywhere else, prime will be 1 over 2 pi I d by d tau, just to avoid multiples of pi in the equations, right? To make them rational, to make all coefficients rational. So it's also known that these equations, this simple first-order system, is invariant under the action of SL2R, right? SL2R, which acts on the system as follows. Tau transforms in a linear fractional way, like this. E2 transforms as a quasi-modular form, and E4 and E6 transform as modular forms of weight 4 and 6. I want to stress that in this construction, A, B, C, D are arbitrary real numbers. It's not SL2Z, it's SL2R, right? SL2R symmetry, right? This is also a well-known fact. Now, it's well known that every function, every modular form f on SL2Z is a homogeneous polynomial in E4 and E6, all right? Then if I differ, so let's write this equation. F equals some function of E4, E6. Let's differentiate. So I'll get f prime equals derivative of the right-hand side. And for derivatives of E2, E4, and 6, I use this. Then in f prime, E2 will appear because it appears here and here when you differentiate E4 and E6. When you differentiate further, E2, E4, and E6 will appear on the right-hand sides. So I'll get expressions for f, f prime, f double prime, f triple prime as certain algebraic expressions, in fact, polynomial expressions in E2, E4, and E6, right? So 4 functions are expressed in terms of 3 functions. So we can eliminate E2, E4, and E6, and this gives a third-order nonlinear ODE, ordinary differential equation for f. And clearly, since the system is a SL2R invariant, this third-order differential equation will inherit this SL2R symmetry. Okay, so let me now, I think...
let me just make a remark. This property with respect to SL2R, it is called Halfon property also. Because Halfon before Ramanujan knew about this differential.
This one, yeah?
Yeah.
This symmetry, okay.
So, and he knew that the action, the space of solution is invariant under SL2R action. So this is mainly Halfon.
Okay. Yeah, and by the way, if if we, from these equations, if we eliminate E4 and E6, it's easy to do, then you'll get the so-called Chazy equation for E2, right? Third order, very simple third order ODE for E2, and it was well known to possess SL2R symmetry, right? Okay. Now, an example. Let's take the modular discriminant delta, which is given by this well-known formula, right? It's a cusp form of weight 12 on SL2Z. And it's well known that this delta satisfies an SL2R invariant third-order ODE, which is due to Reznikov. It's explicitly written in his paper, this ODE, right? Third-order ODE. It's quite, these ODEs are getting quite messy, but what is good about them, they can all be written with integer coefficients, and they are algebraic in the derivatives. They're just, polynomial in the derivatives, right? Polynomial in the derivatives with integer coefficients, right? And also this function delta is known to satisfy this fourth order ODE, ordinary differential equation, right? Which is due to Rankin and van der Pol, right? So you can see that this ODE, fourth order ODE, it has an extra scaling symmetry. If you scale delta, if you go from delta to lambda is just some scaling factor, then this ODE will still hold, because you see each term in this ODE is of degree 4 in delta, right? This, I want to stress that this scaling symmetry is not present in this third order equation, because you see this first term is of 6 degree in delta. This is also degree 6, but the last one, delta to the 7, is of degree 7. You can't scale delta. This equation, third order equation, will not be preserved. So this third order equation has a reduced symmetry, only SL to R. Well, the fourth order, it has GL to R, right? A bit bigger symmetry. Right. And another remark is, if you take this differential equation, differentiate it, and then use this third order equation to simplify the result, you'll get this fourth order equation, right? So in other words, in the language of differential equations, we say that this equation, fourth order equation, is a differential consequence, differential corollary of this equation, right? So in other words, if you differentiate and play with both equations, this one and its differentiated version, you'll get this one, okay? I want to stress that if you just differentiate this equation and leave and take it and take this result, it won't be GL2R invariant, right? Just the differentiated version of this equation is not GL2R invariant. You have to use this equation to simplify the result to get a GL2R invariant equation. Okay, now what is the general construction? Before I proceed to the general construction, let me say a few words about the modularity theory. So it says that every elliptic curve, gamma, with rational coefficients possesses a modular parameterization, which means that there is a rational map from the factor of the upper half plane. And this happens for some level n. There is a congruent subgroup of certain level n such that the factor h by this congruent subgroup possesses a rational map to gamma. So in other words, you can parameterize gamma by, you have a modular parameterization. Furthermore, this gamma has a holomorphic differential, right? One single holomorphic differential, because it's an elliptic curve of genus 1. So let's take this holomorphic differential living here and pull it back. So it will become expression a one form of this type. So it turns out that the pullback of holomorphic differential from here is pi I f of tau d tau, where f of tau is a cusp form of weight 2 on gamma 0 of n with integer coefficients. This is the statement of modularity theorem. So, in other words, this curve, rational curve gamma, can be parameterized by this modular form and its derivatives, right? I will show you formulas. So this conjecture this is the statement of Taniyama-Shimura-Weil conjecture, which was proved by Wiles and Taylor for semi-stable curves, and then in general by their colleagues and students, right? So for instance, let's take this particular elliptic curve. By the way, there is a table of elliptic curves and the corresponding modular forms, all right? And the first element in this table is this curve. It's sort of the easiest example. It comes first in the table. So this curve has J invariant shown here, right? And via modularity theorem, it corresponds to this particular modular form, which is a cusp form of weight 2 on gamma 0 of 11, of level 11, right? So this curve corresponds to this modular form. So now we have the following observation, which I haven't seen in the literature. So if we now, as I said, every modular form satisfies a third order differential equation. I will show you differential equation for this particular modular form. So this differential equation allows you to reconstruct explicitly this curve. So in other words, if you know differential equation for the modular form, third order differential equation, then you reconstruct the curve, right? So there is a kind of direct link between differential equations and elliptic curves for modular forms of weight 2. For modular forms of weight 2. So in other words, this differential equation for f of tau knows the corresponding curve. Okay, I'll show you some examples. This will not be exactly this curve, but something birationally equivalent to it. I will show you at the end. So now the general construction. Okay, this we can skip. It's how Fermat's last theorem was proved. It's just a slide. Suppose that A, B, and C, we prove Fermat's theorem by contradiction. Suppose there is a solution, then you construct this elliptic curve. It was proved in 1990 by Ribet that this particular curve cannot possess modular parameterization. It's not modular. And then once we prove that all elliptic curves with rational coefficients are modular, we get Fermat's last theorem. Right? So this means there can't be ABC such that this holds. All right, now the general construction. Suppose we are given a modular form f of tau of weight k on some congruent subgroup. Doesn't matter which at this stage. So I claim that every such modular form satisfies a third order ordinary differential equation, which can be represented in this form as an algebraic relation among these two objects, ik and jk, which are shown here. Ik is this expression, and jk is this expression, right? So let's look at these expressions. So how they were constructed. Okay, these are simplest differential invariants of SL to R action, right? Of the corresponding SL to R action. So it's straightforward to construct them. There is a general recipe how to construct differential invariants of a Lie group. So this is a second order differential invariant. You see, it depends on K, on the weight. Yeah, and the action of SL to R on F is given by this formula on the last line. This is the action, right? This is the action of SL to R, right? And this is second order differential invariant of this action. This is a third order differential invariant of this action, right? So let's look at IK. First of all, its numerator. Oops, sorry. First of all, its numerator, this expression, right? This is the Rankine-Cohen bracket, FF2. So what upstairs, I have a modular form. This is a modular form. Of the weight, what is the weight? It's 2k plus 4. This the weight of this thing is 2k plus 4, right? But this thing downstairs, formally, if f is of weight k, this expression also has weight 2k plus 4. But this is not modular in general, because you have division 4 over k. You have kth root. So it's not strictly speaking a modular form, right? Same here with the second expression. This expression upstairs is a modular form. It can be expressed in terms of Rankine-Cohen brackets, right? So this expression, it depends on k, and it has weight 3k plus 6, this thing, right? This expression downstairs, it also formally has weight 3k plus 6. But again, it's not modular because of this k in the denominator. It's not. It's an algebraic function. It's a root of a modular form, but it's not a modular form on its own. But it doesn't matter. So there is a theorem that every every SL2R differential equation, SL2R invariant differential equation can be written as a relation among these invariants, ik and jk. There is a function of ik, jk equals 0, which defines SL2R differential equation. Every differential equation which is invariant under this group can be written in this form. All right. In particular, for modular forms, this relation will be algebraic. Right? This will be an algebraic relation. So in other words, with every, so on one hand, I can view this equation as a third order differential equation. If I substitute for ik and jk, these expressions, this and this, right? So on one hand, it's a third order differential equation. On the other hand, I can view this as the equation of an algebraic curve associated to my modular form, right? There is a naturally associated algebraic curve. And we will see that for forms of weight 2, this will be an elliptic curve, right? So let me consider a especially interesting case when case 2. If case 2, then denominators also become modular. So let me show you on the next slide. Suppose that k is 2, right? K is 2. Then I have third order differential equation in this form. F of I2, J2 is 0, where I2 is this thing and J2 is this thing, right? Now both top and bottom in both expressions are modular forms. So I2 and J2 are modular functions, right? And we know any two modular functions are algebraically related. It's a theorem of Hurwitz, right? So f of I2, J2 is an algebraic relation. It's a few line calculation, simple calculation, to show that if you differentiate these, take differential of di2. di2, it means di2 by d tau times d tau, right? This expression. So if you calculate this and divide by j2, you get this simple expression, pi I f of tau d tau. And it turns out, in all examples that we considered, that this expression di2 over j2 is actually a holomorphic differential on this curve, all right? So like in modularity theorem, you see you have parameterization of this curve by some modular form of weight 2, right? And the pullback of the holomorphic differential, this is holomorphic differential, its pullback is pi I f of tau d tau, right? So it's as in the modularity theorem, right? So I will show you some examples later. It's a general construction. Now, a few words about fourth order ODEs, right? So again, let me take an arbitrary modular form of weight k. I claim that every such modular form satisfies a fourth order ordinary differential equation, which can be represented in this form, f of pk qk 0, where pk and qk are certain differential expressions shown here. This is pk and this is qk, right? So these particular expressions, it's for any k, they are modular functions, because here top is a modular function and bottom is a modular function. They can be uniquely expressed in terms of Rankine-Cohen brackets, right? Here and here. So here for all k, pk and qk are modular functions. Two modular functions are always algebraically related, so we get this, right? Of course, you see this pk and qk, they depend only on k. But this equation f, it depends on the modular form. So it's not kind of universal. It depends on f. So if you take two different modular forms of weight k, right, you'll get different f's, obviously, different curves.
So Evgeny, what is the degree of these curves, f curves?
F curve. So that's a good question. To be honest, I don't know. I only know that in all examples that we considered, they are rational. For instance, the curve, the previous curve, f of phi k jk, it was elliptic or rational. It can be higher genus. But in all our examples, this curve is rational and it's covered by the previous curve. There is a covering map from the previous to this one. Yeah.
Okay.
So, unfortunately, we don't have a good geometric meaning for this curve. I don't know. I can't answer. It would be nice to know its geometrical meaning. The only thing I know is that the previous curve, it covers this curve. There is a direct map from the previous curve to this one. In the I don't have this formula on the slides, but in the archive preprint, we have this formula. All right. So, okay, once we have these formulas, let me show you some examples. We calculated these differential equations and their invariant form for various modular forms. So let me show you some examples. Let's take E4, Eisenstein series E4. So it satisfies the following fourth order ODE. You see, it's not quasi-linear, it's quadratic in the highest derivative, right? Quadratic in the highest derivative. So this is explicit form of this third order ODE. As I said, okay, all coefficients are integers and all monomials in this equation are algebraic expressions in the derivatives. Like it's an algebraic equation. Then its invariant form, if you write this in terms of the invariants, it becomes quite short. In terms of I4 and J4, you get this. It's a nodal cubic. It's the equation of a nodal cubic. It's rational, right? This is a rational curve. And the fourth order ODE, I'm not writing it explicitly. It becomes long. All these ODEs are quickly becoming quite long. But in terms of the invariance, it's relatively simple, right? It's in fact very simple. Just a linear relation among the invariants. This is the fourth order ODE. All right. And the curve, the corresponding curve is just a line. Here, it's a nodal cubic. Here, the curve is a line. All right. Not very interesting, but it will get more interesting later. So, Eisenstein series, Eisenstein series E6. So there is when we calculate, so it's actually, if you write it in terms of the derivatives, this expression becomes quite long, as well as this one. Right? But in terms of the invariance, it's relatively simple. And Reznikov, who obtained differential equation for E4, he said that in the same way you can get differential equation for E6, but the computations are quite long. Obviously, everything was done by hand at his time. There were no computers. And there is no point of doing this computation without any compelling reason. This is what Reznikov writes. But in terms of the invariance, it's a relatively short expression. And you see, it defines an algebraic curve of degree actually 6. You see, I6 will be to the power 6. This is a curve of degree 6, but actually it's singular. And this curve is rational. It's a rational curve, but with singularities. Nodes, double points, cusps. Sorry, double points and cusps. And then fourth order ODE is given by this formula. If you write it in terms of the derivatives, it will be one page, right? But in terms of the invariance, it's simple. And it's a conic. It's the equation of a conic on PQ plane, right? Okay, let's move on to modular discriminant. I have discussed this equation. This is the Reznikov third order equation. And this is its invariant form, right? Invariant form, a cubic form. It's a cubic curve, right? And then this is the fourth order ODE. And this is its invariant form, very simple. Q12 is 6. This 12 is the weight. Delta is weight 12, so it's Q12 is just to indicate the weight. I see you J12, I12. 12 indicates the weight. So you see invariant expressions for these differential equations are very simple. All right. Then Jacobi theta constants. So here are three Jacobi theta constants, theta 2, theta 3, and theta 4. It was Jacobi who derived a third order equation for theta constants. And this is it. Here it is. This is a third order nonlinear ODE derived by Jacobi. And it has, so each of these theta constants satisfies one and the same equation, right? Namely this one. And in terms of the invariants, you have this, right? This 1/2 indicates the weight again, because theta constants are modular forms of weight 1/2, right? So again, this is a nodal cubic, rational. It's a rational curve, rational cubic. And the fourth order ODE, okay, I actually haven't seen it in the literature, but it's straightforward to get it. This is a fourth order ODE, and it's, again, in terms of the invariants, it's a very simple relation defining a line in the PQ plane, just a line, right? Okay, further, a few more examples. Eisenstein series E13. Actually, this example will appear later in the classification of integrable Lagrangians. In fact, through this example, I became interested in modular forms. Because I got this differential equation, fourth order differential equation, in the classification of integrable systems of some kind. And then someone told me, my colleague told me, okay, general solution of this equation is a modular form, and this is how I became interested. Anyway, so E13 of tau is this, it's a theta function actually, yeah, it's this equation. This is its Q expansion. It satisfies a third order ODE, which is here. Its invariant form is this, which is again a nodal rational cubic, right? Nodal cubic. And the fourth order ODE is this. And in terms of the invariants, it's just this relation. This index 1 indicates that E13 is a weight 1, level 3 modular form. Okay? Okay, now more interesting, something more interesting. So let's take, there is a unique cusp form of weight 2 on the congruence subgroup gamma 0 of 11. And here it is. This is the formula. All right, and it has a label in the LMFDB database. It has this label. So everything is known about this modular form. All right. So this modular form satisfies this ODE, third order ODE. Remember, J2 and I2 are differential invariants. They're expressed in terms of first, second, and third order derivatives of this f of tau. So this is a differential equation written here, represented as the equation of an algebraic curve. It becomes a differential equation when you substitute here the expressions for I2 and J2 in terms of f, right? So, but as a curve, you can check that it has genus 1 and J invariant equal to this expression. So there are Maple programs. If you type this curve and ask Maple, what is the genus? Maple says genus 1. What is J invariant? Maple says it's this, right? Although this curve is singular and high degree, this is a high degree curve. You see its degree, it's 2 plus 3 plus 1, degree 6, right? It's a curve of degree 6. Still, it has genus 1, right? Because it has singular points, right? And remarkably, this curve, this J invariant, this value for J invariant is exactly the same as the value of J invariant for this curve. For this curve in more or less Weierstrass normal form, which corresponds to this modular form via modularity theorem. So I mentioned this in one of the first slides, that this curve, this elliptic curve, is uniformized by this modular form, right? And our differential equation defines a curve with the same J invariant. So it means that this curve is actually birationally equivalent to this normal form because they have the same J invariant. If two curves, algebraic curves, are birationally equivalent, they have the same J invariant. And this means there is a birational map between them, and it's shown here. So here are expressions of I2 and J2 in terms of X and Y. This curve is in terms of I2, J2 variables, and this is in terms of X and Y variables. So there is a map from this curve to this curve, rational map, which is given by this formula. Remarkably, this map can be inverted, so it can express X and Y in terms of I2, J2. It's a little bit more complicated. It's here. X is this, Y is this. So this shows that these curves are birationally equivalent. So in other words, let me return back. In other words, differential equation for f of tau, this differential equation, written as a curve, it knows the elliptic curve that corresponds to this modular form via modularity theorem, right? It knows this curve. Once you have this, you can bring this. There is a general program again. I think you can do it in Maple. You can find, you can bring the equation of an elliptic curve. You can resolve its singularities and bring it to this non-singular model, right? It's kind of, there is a universal, an algorithmic procedure how to move, how to map this to this, right? And in fact, these formulas were found by computer. Okay, and if you calculate this di2 over j2, it turns out that this is holomorphic differential on the previous curve, on this curve. If I calculate holomorphic differential of this curve, then I get di2 over j2, very simple answer. And it equals pi I f of tau d tau, right? As in the modularity theorem. Now, what about a fourth order ODE? Remember, fourth order ODE is expressed in terms of P and Q variables. There are invariants P2 and Q2. And this fourth order ODE is here, right? Coefficients are quite horrible, but this, and you can check that this curve is actually singular rational curve. And there is a covering from the genus 1 curve to this rational curve, right? I'm not writing it here. And this is very typical. In many other examples, we got the same picture. Third order ODE defines a genus 1 curve. Fourth order ODE defines a rational curve. Okay. Let me show you a few more examples. A modular form of weight 1 on this particular subgroup, gamma 0 of 63. So in our, we calculated quite a few of them. I'll just show you, I'm showing you a selection. And in all our examples, the genus of the corresponding curve was 1. And we were trying to find an example just for out of curiosity that would have genus 2. And we found one. And the easiest of them occurs, the easiest we managed to find. Maybe there is an easier one. We took a modular form of weight 1, a cusp form of weight 1 on gamma 0 of 63. So weight 1, not 2, as in the previous example. So, and this cusp form is given by this formula on gamma 0 of 63. So it has a label in LMFDB database. This is the label. And the third order ODE is written here, right? Expressed in terms of the invariants, right? Remarkably, this curve of very high degree, has genus 2, and its Weierstrass normal form is this. So it's a genus 2 curve, right? So just out of curiosity, there are examples where modular forms of weight 1 uniformize higher genus curves, in particular genus 2 curves. I don't know the answer to the following question: which algebraic curves with rational coefficients can be uniformized, can be parameterized by modular forms? For genus 1, okay, the answer is every such curve can be parameterized by genus 2 modular form. But in general, suppose I have genus G curve with algebraic with rational coefficients. In which case can it be uniformized, parameterized by a modular form of some weight and some level? I don't know a general answer. Probably it's known, it's understood by experts, but okay, I couldn't find this in the literature. Okay, one more interesting example. Let's take a modular form of weight 1 on gamma 0 44. Okay, here is the equation. This is the formula for f. Right, again, it has a label in the LMFDB database. Here is the label, and this form satisfies a third order ODE, which is written here. Right, this is a third order ODE. Remarkably, this curve is exactly the same as the one I started with on gamma 0 of 11, right? Exactly the same curve, right? So it has a genus 1 and the same J invariant. So actually it's identically the same curve as in the example on gamma 0 of 11, right? So this example shows that one and the same genus 1 curve, it can be parameterized by a modular form of weight 2 via modularity theorem. And it also can be parameterized by a modular form of weight 1, right? In this way. So one and the same curve. Okay. And then I want to discuss an example of how differential equations of modular forms appear in the classification of integrable systems. So in this paper we looked at the general class of first order Lagrangians of this kind. So the density of the Lagrangian is just some function of first order derivatives. ux1, ux2, ux3, no assumptions on the function f. F is just some function. So if you write the Euler-Lagrange equation for this Lagrangian, you'll get a second order PD, right? And we may ask, for which functions f will this PD be integrable? Let me skip. What does this mean? All right? It's a separate story. What integrability means in this context, let me skip this, but there is a precise, it can be made, all these questions can be made precise. In general, integrable means to some extent solvable, so you can construct solutions, you can construct a Lax representation or some other, or there are many different properties integrable systems have, and most of these properties are equivalent. And in fact, for this particular class of Lagrangians, the requirement of integrability leads for a system of differential equations for this f, for the Lagrangian density, for this function f, all right, over determined involutive differential system. And it was proved, it was observed by my colleague Alexander Radesky that this general f is actually a modular form of 3 variables. And then this was made precise in our preprint with Clery, Radesky, and Zagir. It was realized that this function f is actually a Picard modular form of its arguments, not precisely Picard modular form. It's related to Picard modular forms, right, in some precise way. This is still a draft, but okay. It's available on Don's website, webpage. Okay, but let's look for a simpler class of densities, where this function f is ux1 times ux2 times some function of ux3, some function. And let's write down the integrability conditions. I have a system of integrability conditions for f in general. So let's apply these integrability conditions for this particular ansatz. Then it turns out we get a particular ODE. We get a fourth order ODE for this function f, which is written here, right? And okay, of course you don't remember, but it's precisely the fourth order ODE satisfied by this Eisenstein series, all right? At the time when we obtained this ODE, when we obtained this ODE, I had very little knowledge of modular forms, and I couldn't even anticipate that modular forms will appear as the answer in what I do, right? But okay, my colleague Sasha Odesky, he explained, he kind of solved this equation in modular forms, and he obtained this solution, right? So it became clear that the occurrences modular forms in the theory of integrable systems is not accidental in this particular case, and they occur in many other similar circumstances. Right? Okay, so now we have an option. I finished sort of my talk, and the rest is Jacobi forms. Probably we can stop here. What do you think? I have something like 3 slides about, or maybe no, maximum 5 slides about Jacobi forms. So, but it will take some time. Maybe it makes sense. What do you think? I have 2 minutes. All right. Let me then just flash a few more slides. Jacobi form is a function of 2 variables, modular variable and abelian variable, which satisfies this transformation property. Okay, you know this better than me. It turns out that every Jacobi form, f, satisfies a differential system of partial differential equations. This time we have partial differential equations because we have 2 variables, tau and z. It's not an ODE anymore. It's a partial system of partial differential equations. And I will just show you examples without any general theory. I'll show you the examples. So let's take Jacobi form, weak Jacobi form phi minus 1, 2. Minus 1 is weight, 2 is index, right? It's given by this explicit formula. Theta 1 is Jacobi theta function, delta is modular discriminant. This is precise expression for phi minus 1, 2. This is Jacobi theta function. So this function f, this one, it satisfies this differential system. 4 differential equations. So look, all third order derivatives of f are expressed in terms of low order derivatives. For instance, f tau tau tau, third order derivative in tau, is expressed in terms of second order derivative. F tau tau z in terms of second order derivatives, and so on. So this system is involutive, so it's consistent, although one function, there are 4 equations for one function, they're all consistent, right? And second, this system is of finite type. So, because all third order derivatives are expressed in terms of low order derivatives, such systems are called of finite type. And it's invariant under the Jacobi group, right? So it's like, and this f is a generic solution of this. Up to the action of Jacobi group, f is the unique, this thing is the unique generic solution of this system, right? This is one example. Then I'll show you one more. Let's take Jacobi theta function. It's also a Jacobi form of index 1/2 and weight 1/2. It's known that theta function satisfies the heat equation. It's the heat equation. But it's less well known that this Jacobi theta function satisfies this equation in just z variable. It satisfies this equation as well, which is quite simple. And these two equations, the heat equation and this ODE, they're consistent. So this system again is involutive. It has a little bit different structure from the system on the previous page, but actually it can be obtained by the same recipe. It just turns out that the structure of invariants of Jacobi group, it depends on index and weight. And when the index and weight are 1/2, the structure of invariance changes. That's why the form of the system changes, right? But actually it's the same philosophy behind. So, okay, I haven't seen this equation in the literature, right? Although it's a very classical object, Jacobi theta function. This equation I haven't seen. There are maybe equivalent versions of this system, but they're not written in this simple form. Okay, and one more example. And this is my last slide, by the way. Weierstrass P function. It's a Jacobi form of weight 2 and index 0, P of tau z. So everybody knows this equation in Z. PZZZ is 12 PPZ. Right, this is a well-known equation. But these two are less well-known. That P tau tau is this expression. P tau ZZ is this expression, where this F phi, this phi appearing here and here, is this explicit expression. Again, this system of three equations for Weierstrass P function is involutive. It's of finite type, and it's invariant under the Jacobi group. So in fact, Weierstrass P function is the unique solution of this system up to the action of Jacobi group. All right, and this is the case for all Jacobi forms. So, but formulas are becoming quite messy for other Jacobi forms. All right, here I stop. Thank you very much. Thank you.
Evgeny, one question.
Right.
Is it possible to do in the other way around? For example, take a modular elliptic curve with
Yes.
With well-known eigenform. I mean, take one example from this LMFTB side, and
Yes.
try to construct a differential equation out of this.
But this is exactly what we did. We took the first few entries in this table, in modularity table, right? So we take a particular elliptic curve, we take the corresponding modular form of weight 2, we construct our differential equation. It gives us an algebraic curve of genus 1 with singularities, which is birationally equivalent to the curve you started with.
Yeah, but you construct, and you have checked, you have constructed also the differential equation. What I mean that just from the picture of the elliptic curve, the way you guess what would be the differential equation. I mean,
no, unfortunately not. We only know it will be birationally equivalent. It will be an algebraic curve birationally equivalent to the curve we started with, but not exactly the same.
So with the structure of this birational equivalence, you know how many singularities in the other curve
This can be, yeah, if you have an explicit equation of the curve, you can analyze everything.
Yeah,
you can analyze the number of singularities. I think we haven't done this. We haven't done this in detail. We just, in fact, what I'm saying is not a theorem. We don't have a theorem that we always get something birationally equivalent to something from the modularity table. It's an observation. We looked at several first entries of this table, and this is what we see. I'm sure it's a general fact, right? But I don't have a proof.